We're now going to take a look at the control strategy capabilities of a station. So as we saw with the scheduling lab, it is possible that we can create new folders at a top level, give it an appropriate name. Then these folders have a wire sheet, and we can use that wire sheet to create points and do the control strategy. But because we've got wire sheets in other places in the station, it is possible to distribute your control strategies in different places. Again, it's a bit of a design consideration of why you need to maybe put them in different places, and maybe it is easier to keep it simple and keep them all in a central place, then it's easier to find stuff later. But I'm just going to go into the wire sheet of my plant room folder, and I can see all the points, so I'm just going to arrange those up, and they can all be moved around. And then we're going to open up a palette, and the one we're particularly interested in this case is called kit control. So kit control has a lot of items in here, and there are logical items for logical ands, logical ors, a not or an invert. Then there's lots of mathematics functions and timers, and then there are some HVAC related items that we're interested in. So we've seen the thermostat earlier. The loop point is a PID loop, and that's what we're going to look at in this lab. So we're just going to take a quick look at the PID loop and what that looks like, and then we're going to get started with setting this example up. So on my wire sheet, I've just done a little bit of organisation. I've put my inputs on the left. My outputs are over here on the right, so I can use this little preview window to click and drag and move around the wire sheet. The wire sheet will get to a certain size and then become very hard to follow what's going on. So if you've got a really big strategy, it's better to break it up and use folders to have segments of control pieces like time schedules and demands and safety interlocks, frost protection, calculations and outputs and so on. For this example, we're just going to stay at this level. And from a palette, I'm going to select the loop point component, drag it in, give it an appropriate name, and then again stretch it out a little bit. Now there's not much to see on the wire sheet, but if I double click, then there are a lot of properties that are available in here. We'll go through those in a second. If I return to the wire sheet, I can right click and do pin slots, and then I can start to pin out some of the more interesting items in here. So the loop enable, the control variable, set point, execution time, the loop action, the proportional constant, integral and derivative, and then I'm just going to leave that there. And again, if I double click and go in, we can see all the properties. So the component has a facet for its output. This will be a percentage, so miscellaneous % symbol. Not going to change any of these other properties for now. It's got an output value. It's got an enabled state. So this is binary from maybe from a time schedule or something a bit more interlocked. Input facets. So what is the item that is being controlled? Is it temperature, humidity, pressure? So we're going to do a temperature example. Controlled variable is what we're looking to control. Set point is the target. Execution time refers to how often this PID loop is going to recalculate its output. We'll talk about that a bit more in a minute. The loop action, like we saw with the thermostat, has direct or reverse. So in this example, it's kind of, is this a cooling application, direct action, or for a heating application, a reverse action? So when the control variable is below the set point, the loop output will start to do something. And then we've got tuning facets, which again are going to be a percentage. And then we've got these settings: proportional, integral, derivative, bias, maximum output, minimum output, and a ramp time. Now, this lab doesn't really go into detail about the methodology of using a PID loop. We're just demonstrating that Niagara has that component available in the toolbox and how we can use it on a wire sheet. If you right click on the component and go to Views and Guide Help, it will pull up the helper documentation. It will give you explanations about all of those settings and what they actually mean. But there is an assumption that you are from a controls background and understand the application of a PID loop already. We are just going to look at a real world example in the next section of the video just to give a bit of brief information about what it is we're going to do. So this graph is an example of a PID loop being used in a Niagara 4 station. And I just want to talk about the differences. So we saw the thermostat component used in an earlier lab. And the thermostat is very common in BMS applications, but it's just a binary output, which means a piece of equipment is either off or on. So in a heating application, the heater's enabled or it's not. And if we looked at the temperature graph, it would be like a seesaw or maybe a sine wave where the temperature goes up, hits the set point, the heater turns off, the temperature starts to drop, it'll go to a certain level, the heater will come back on, and you end up with this constant cat and mouse of the temperatures up and down above a set point, but never actually maintaining the set point continually. And then we have other BMS applications where we need much finer levels of control. So it could be speed control for a pump, speed control of a fan in a ductwork, pressure control applications, or it could be a heating application. So it could be a heater in a space or a heater on a handling unit where we need to be able to control the heater based on an actuator or a valve, where we have a 0 to 100% control over a 0 to 10 volt signal. And in these sorts of applications, that's where we're going to use the PID loop to achieve that. So it has three key settings that we're interested in: the P, the I, and the D. So that's proportional, integral, and derivative. So in the vast majority of BMS applications, we probably maybe only see the P and the I being used. Not very common that we see derivative being used, but there's no reason why it can't be. But in this example, this is just proportional and integral. So when we say proportional, what we mean is that if we've got a set point, and we'll keep the numbers quite simple, so we want to achieve 21 degrees Celsius, the temperature is below that by whatever units. The proportional setting, if we set it to 25%, that means for every degree of error, so every degree we're below set point, we get a 25% output. So 1 degree below, 25, 2 would be 50. At 4 degrees below set point, we get 100% output on the loop. The problem with proportional only control is that you'll never actually hit the set point, because what will happen is that the closer you get, so the temperature starts to rise, the less output we have on the proportional basis. So the temperature rises from the 4 degrees below to 3 degrees, 2 degrees, 1 degree. At 1 degree below the set point, we're down to 25%. And then the closer we get to the set point, the less the output will be. And what will happen is the temperature will approach the set point, never really get there because the output's too low, and it'll start to drop off again. So it's like an analog version of the thermostat. So we have to use the integral action to get us over the set point. So the integral action is a time-based parameter where it's looking at the error between the set point and the measured value, and then over time it's adding some more output into the calculation. So you do need to be careful, because in other systems the integral action may be a time-based parameter in minutes or seconds. So in the trend world, it would be in seconds probably. But in Niagara 4, the integral action is classed as a repeat per minute. So how many times do you want to add the proportional constant in per minute? So if we set it to 1, it will be 1 minute. And then if we set it to 0.1, it would be 10 minutes. And in this graph, we see this in the real world example. So we've got a handling unit here with a supply humidity. The blue line is a measured humidity in the ductwork. The purple line is a target or the set point. And then the green line is the controlled output to the humidifier. So what happens is that the humidity is bobbing along the target. And then all of a sudden, the humidity level drops down very quickly. And a result of that change in measured value, the PID loop recalculates the output, and the output goes from a steady 66% up to 100% because we've got such a degree of error between the measured value and the target. And that output's maintained for a while. And then all of a sudden, the measured humidity starts to really shoot up. And we get this overshoot that happens. And as this is happening, the PID loop is constantly adjusting its output. So the output quickly comes down. And then we get an undershoot that happens on the measured humidity. And again, the PID loop is detecting that error and readjusting itself. So it starts to output more. And then it starts to bob along the line steadily until a repeat of this problem. So the problem in this example is that the humidifier is flushing its water out, therefore it can't produce any steam, and then we get this drop in humidity. So this example here, and then this overshoot and undershoot is a typical example of a PID loop in action, but this is just proportional and integral action only in this example. So we're going to take a look at how that works in terms of Niagara 4 in 1 second. So I've returned to my plant room wire sheet. I've got my Modbus inputs on the left, my outputs on the right, and I've got a PID loop component that's here now. Now there may be situations where you want to simulate some strategy because you're not connected to the I/O and you want to just prove something's working. Now we can insert a numeric point and we've seen that these have override actions where we can set a value. But if we were wanting to do a simulation, we'd have to keep changing the value, and that could become a lot of effort to do that. So in my kit control palette, I'm going to come down to the Util folder, and I'm going to use a component to simulate a temperature. So I've got the ramp and the sine wave. They're very similar in terms of the application that they offer. They have the same settings. I'm just going to pick one of them. So I'm going to drag the ramp in. I'm going to give it a name. And then, again, each one of these components we bring in from the palette is going to have its own property sheet. So the temperature simulator has a couple of settings. So it's got a period, a time range over which it's going to run over the settings. And it's got the amplitude and the offset. So right now this has got an offset of 50 and an amplitude of 50. So the offset we think of as like the middle line, and the amplitude is how much above and how much below the offset it's going to go to. So in this example it will go from 50 up to 100, back down to 50, down to 0, back up to 50. So if I put some other values in just for a quick test, if I put 21 as the offset, 4 as the amplitude and press save, then I'll achieve a value range of down to 17 up to 25 over a 30-second period. Again, I can apply a facet to this component, degrees Celsius. So I'm just going to make this to run over 1 minute. I'm going to give it an offset of 60, and an amplitude of 20. So that will give me a number range of up to 80, down to 40, again over that 1 minute period. And then I'm just going to return to my wire sheet. So I can see now that the live output of that block is happening. And I can take that and I can use it to link up to the PID loop in a minute. I'm also going to want a set point parameter. Now in the lab notes for this lab it talks about using a constant here. We've got a numeric constant which you can drag in and call it a set point. If I go into the property sheet here, there's very little to see. It has a right click action and set. Now I don't particularly like these numeric constants because they're very basic and not that functional. So in terms of a set point block, I would always use a numeric writable, purely because it's got some override functions available. So the emergency override and the timed override. I'm not using the input slots on this one, so I'm going to go down to pin slots and just hide those away to make it a bit more neat. And then I'm going to give that a value, right click action set. I'm going to set that to 70. And then again, I might want to apply a facet of degrees Celsius. And because it's a set point, you may want to define a minimum and a maximum value to prevent operators from putting in values that might cause a problem. I'm just going to leave it as it is. And then, like I said, I can start to feed these values into the PID loop, but we're just going to take a look at those settings again before we do that. So I'm just going to go back into the property sheet of the PID loop with a double click. So I previously set some of these things up, the facets on the output, the loop enables there. And these items, sometimes the names are not very helpful, so control variable and set point. So we can actually go into the slot sheet, either through the AX slot sheet or the HTML5 property sheet. And we can start to rename some of these components. So control variable, I'm going to call boiler temp. And set point, I'm going to call boiler SP. Loop enable, I'm going to call schedule. So now when I return back to the wire sheet view or the property sheet view, these items have been renamed. And then on the wire sheet, we can see what they actually are. So it takes a little bit longer to set up, but it does help you to document what's going on, especially if you've got like a logical AND, a logical OR, a minimum, an average component. You can label where the values are coming from. So I'm going to go and find my schedule I created earlier. I'm going to right click on it and go link mark. I'm going to come to my loop and go right click, link from the output of the schedule to the loop enable, or the schedule block now, the schedule that I renamed. So it's got an enable signal now. Temperature simulator, I'm going to feed into boiler temperature. Set point, I'm going to feed into boiler set point. Now, the output of this PID loop is still not doing anything, so I'm just going to go into its property sheet again. And the proportional constant here, I'm going to set to 10%. So that means that for every unit of error that I have, the loop should be outputting a signal. Right now it's not, because the loop action is set to direct. I'm going to make this reverse. So reverse means that when the temperature is below the set point, in this case, the loop output will become active. So it's a heating application. So we're 20 degrees away from set point, and we've got a 10% output. I could change that down to 5%. So now for every degree of error, we get a 5% output on our loop. And then that's changing quickly. Once we go above the set point, the output's up at 0. I'm not going to use the integral or the derivative action because they just make it too complicated for this example. It's a very basic wire sheet example that we're going to use. And again, that temperature is coming below and the loop output is becoming active. And we can see that from the wire sheet. So we can take that output and right click and create a new component here. Boiler signal. Take that output into input 16. Now the only reason I'm using a numeric writable is that, again, in the future if I want to do some maintenance or testing activities, this has some override actions available. What I'm going to do now is I'm just going to right click on the PID loop and go to views, and it has very similar views to every other component we've seen, but the one I'm interested in is the chart view. So this component does not have a history extension on it, which means that this chart will be a live plot of the output of the PID loop. So over time this output is going to start to update. And what I can do as well is from my folder I can go and find another component, in this case the temperature, and I'm going to drag that in, and then I can have a multi-chart plot going on. So again, this temperature simulator does not have any history extensions, which means that every time the component updates, the chart should start to match. So there we go, it's starting to multi-plot against each other. In the configuration here, I could go and change the colours. So I could have red for my temperature, and I could have green for my boiler signal. And it allows me to have a live output. And in a real world application, this will be very helpful for starting to try and do some loop tuning to try and get the properties, so the proportional level and the integral level of the PID loop, correct, because when we don't get them correct, what we'll see is a very wildly out of control loop where it's hunting. So the output of a loop is constantly adjusting, maybe too aggressively, off and on or up and down to achieve the desired result, but it never actually works because it's not configured properly. So a live plot just allows us to watch what's going on.